Yeah, thank you, Mr. Chairman. Thank you very much for the introduction. Welcome to my talk. I think, the title is here, The Influence of Thermomechanical Treatment on the Very High Cycle Fatigue Limit of High-Strength Bearing Steel. And I will deal with the questions how to increase fatigue limit, fatigue lifetime by a given method here. And to increase the fatigue lifetime, you have to deal with the distinct failure mechanisms. So we will look at the failure mechanism of this high-strength bearing steel and then apply a special method to increase the fatigue limit. In principle, I think I don't need to tell you something about fatigue even directly after lunch. We know fatigue can happen in a lot of components, even daily use components. So it's important to dimensionally, cyclically load a part in a proper way. If you do it for a given lifetime and you do any mistake, it might happen that the parts fail. So a good idea is to deal with the fatigue limit and to do the dimensioning for eternity. And if you do so, stairs can last nearly eternal time here in the so-called eternal city. Exactly. But this is a very robust construction, and we usually deal with more efficient constructions, and therefore we have to think how to have optimum in fatigue limit. And the aim is to have safer parts, to have sustainable use of materials. In this view, we have used a material here, a bearing steel, which is optimized regarding his fatigue limit since more than 100 years, 100 chromium-6. These are some results from my working group. And we just have a look on the failure mechanism here. As you probably know, in short lifetime, we get usually failure from inclusions at the surface of the material. If we decrease stress and increase lifetime, failure moves to the inside of the material due to different crack propagation, different probability of failure, and different stress intensity factors at the inclusions. And when we look at very high cycle fatigue, this failure from an inclusion is usually connected with the formation of a fine granular area, optical dark area, directly at the inclusion. Just a side hint, we even did this with artificial defects to simulate at the surface with and without vacuum, and then it was even possible to get such fine granular areas. So we don't observe any very high cycle fatigue failure without these fine granular areas. And what is the mechanism behind this? Therefore, are a lot of postulated mechanisms from different authors. Even our chairman has a very famous model here, and even my group tried to set up a model. I think we have some scientific differences in this point because we think first we have grain refinement, then the crack, and other models vice versa. Let me look at our model here. We think that at the inclusion during the cyclic loading, we have cyclic dislocation, slipping, and with time we get cell formations, we get grain refinement. This grain refinement causes a localized, local reduced stress threshold for the stress intensity factor for crack growth. So a crack can start from the inclusion, grow through these fine grains, and then the process is started again in front of the crack. This continues until the crack reaches a given limit, and then the threshold value of the material for long crack growth is reached, and we get the fisheye formation. Now, when we think of how to increase very high cycle fatigue, we can think of, with our model, we can think of how to stabilize the dislocation structure. If we get the dislocation structure stabilized, we can hinder the further processes, or at least it could take a longer time that these processes happened, and so we could increase the fatigue limit. That it, in principle, first this, how do we think that we are able to stabilize locally around the inclusions the the dislocation structure, what we do is a thermomechanical treatment at the temperature of maximum dynamic strain aging, applying some cycles, some fatigue cycles in principle, but very small amount, like 5 cycles per step, and increase the load stepwise to specially modify the area around the inclusions. And what happens with the dislocations in this case is that we, by increasing the temperature, enable carbon atoms to diffuse around in the material, and they are pinned then at the otherwise around. The dislocations are then pinned by dislocations carbon atoms. I think I have a little bit more time than I just don't have to run that much. So we stabilize with this method the dislocations by carbon atoms at the core of the dislocations. That this process in principle works was content of my PhD work some years ago. We did it for high cycle fatigue with alternating bending, and we saw from the black line, which was the baseline for martensitic state of the 100 chromium-6 bearing steel, and it was able, with a special treatment with this increased stress amplitudes during the treatment, to increase the fatigue limit after the treatment. Here, about 13% increase we were able to find out. Of course, if you see, we did this with 25 Hertz. Nobody wants to do very high cycle fatigue with 25 Hertz, of course. So what we did, we investigated same material, but now with the typical specimens for ultrasonic fatigue testing. And here you see, and this was the wrong. This is really, you can see the stress distribution along the longitudinal axis of the specimen. So what did we observe with this ultrasonic testing? This is again the baseline for the material. You see a large scatter due to the dislocation size and position distribution. And applying the treatment here leads to some increase, about nearly 100 megapascals for the fatigue limit at 10 to the power of 9 cycles to failure. And if you look to the lifetime, it's still a lot of scatter here, which is not so, so a really good result. But then we looked at the specimens and recognized that all the specimens which went through the thermomechanical treatment showed, like you perhaps can see here, showed an off-centered fracture, while most of the black dots here, which were not thermomechanical treated, showed nearly central failure. So we thought what might be the reason for this. And again, we have to look at the stress distribution. This is the black line here, which gives us the stress distribution along the specimen. And we recognize that always the fracture happens, in this case, somewhere where the stress is significantly reduced due to in comparison with the area in the middle of the specimen. And what we have plotted here is the failure, is the stress at the inclusion where failure happens. So if we have such a failure, we plot here a stress which is the value at the position of the inclusion. So we recognize, okay, if we have off-centered failure, obviously in the middle of the specimen, there might be still inclusions and they didn't fail. So the question is, can we more calculate what these inclusions had, which they could withstand? And therefore, we calculated the maximum stress in the middle of the specimen for all these fractured specimens. And you see now with the open triangles that some points, when we plot the maximum stress in the specimen, which did not lead to failure, so this area here where we had no failure, are now, for instance, for this specimen, this is the failure position, and this is in the maximum position of the specimen. So it looks quite good for the thermomechanical treatment. Then to see whether whether we suppose it correctly that there are additional inclusions, we wanted to look at the inclusions distribution. Unfortunately, my PhD student was get married and get a child, and then we have not done it yet for this material, but we did it for a very similar steel. This is hidden behind the zoom sign. We did serial cuts of these areas here and recognize there are a lot of inclusions. And if we compare the stress intensity factor at the inclusion where failure happened with the stress intensity factor at the inclusion in the middle of the specimen, this is sometimes, not sometimes, it's always higher than at the position where failure happens. This leads us to the conclusion that we were able to significantly stabilize the local microstructure within the middle of the specimen and shift the failure to other positions where the thermomechanical treatment was not that efficient. Okay. That's all. I hope it fits from the time. Our thermomechanical treatment can improve the fatigue limit even in very high cycle fatigue by dislocation pinning. The inclusions have a higher, we found inclusions which had higher stress intensity factors than those which failed. And we didn't found any grain refinement or crack initiation within this volume in the middle of the specimen. We have to prove it now with the inclusions of the 100 chromium 6. And with this, I want to thank you for the attention and our partners, especially the Institute of Applied Materials at the KIT, which carried out the thermomechanical treatment for us. And my co-author is here, this guy, Jan Sippel, or in the meantime, he is called Jan Metternich. Thank you.